I really am super, super happy that Tim's agreed to keep coming along to do these sessions for us. So we're following up from the workshops he did around New Zealand at the end of last year. And we have a focus on mathematical modelling this time, and we'll be looking at data next time. So I'm going to stop screen sharing and I'm going to hand over to Tim, and I'm going to leave it in his capable hands.
Great. Well, thank you, Pip. And I am so happy to see all of you and to be with you. And I'm going to say this afternoon, as you can see from the clock on my wall, it's just after 4 in the afternoon and it's still Friday. So here I am in California joining you. I really enjoyed my visit to New Zealand in November and December, where I met many of you. Maybe not all of you. I don't recognize all the names, but I recognize some. And so I'm going to say in advance that today we are going to talk about mathematical modeling in the geometrical context, which is one of the things that we did in the previous workshops. If you were not in the previous workshops, that's okay. You will be able to catch up. But this, if you were in the previous workshops, this will give you some additional activities and insight into what was going on in that book that many of you received or purchased. And we will be using CODAP, the Common Online Data Analysis Platform, to analyze data. So this is mathematical modeling in a geometrical context, and we're going to connect it with data. And we're going to take the data, make mathematical models for the data. If you've never used CODAP, you will be okay, but we're not going to stop and teach you CODAP in this brief workshop. But what we will do is make sure that everybody has access to CODAP, and I have written the URL on this whiteboard here. We can see we're in my kitchen, and I hope you can all see it. And somebody let me know if you cannot read that. CODAP.concord.org/app. So Pip,
clear.
Is it legible?
Yes.
Great. Great. And so if we were in person and new people showed up, I would, of course, ask you to tell the person, help the new people by telling them the URL. But we are having new folks appear. Yes, kia ora, everyone. And actually, yeah, good. And in the morning, it's Morena, right? So we're going to be at codap.concord.org/app in some window. But before we get there, I would like to talk to you a little bit about what the overall idea is. What's the modeling plan? And the modeling plan is there's going to be a geometrical diagram of some kind. And we are going to take measurements in this diagram. And I have here my 3-meter tape. I'm gonna measure with this, and I'm going to measure very imprecisely. You might think that I am modeling being a student, as students sometimes measure very imprecisely, but also it's because I'm standing up and writing sideways, but also because it's data. Most data are not super precise. You might look at what I'm about to do and say, oh, if I used Geometer's Sketchpad or GeoGebra, I could get very precise measurements. And that's absolutely correct. But I am not interested in precise measurements. I want measurements that look more like data because students need that experience. So let's begin with a geometrical situation right now, and then we're going to take some data and we'll use CODAP to analyze it, and then we will once again see this. So if you've just joined us, see this URL, get a window with that. But meanwhile, I'm going to I'm going to copy out of the book a geometrical context. I'm going to start with a point P, and I'm going to draw a ray going this direction. I'm going to draw a ray going this direction. So I've got 2 rays. It does not matter what the angle is between the rays. And now I'm going to connect the 2 rays with line segments. And so here's one line segment, right? And I'm going to add a few more line segments that are parallel to this line segment. And I'm just doing it freehand. So are they exactly parallel? No, of course not, but they're kind of parallel. So here's another one. And here's another one. You can see I'm deliberately making them not evenly spaced. Oh, let's put, that's enough. I mean, if you're a student, you might make more. And if you're there with a piece of paper, and we can use my data, or you can have done this yourself on a piece of scratch paper, because you will have a ruler of some kind. Here's one from me, and a pencil. And so you just make them more or less parallel. And so now I'm going to look at this and think about, we don't quite have enough, we don't have few enough people that we can just open it up to let you tell me what's going on. Imagine that if we were in a classroom in real life and we were facing each other, or we were put out into breakout groups, which we could conceivably do, but let's not for speed. We would discuss this and say, oh, what kinds of relationships can you see in this diagram? And remembering that what we're going to do is we're going to measure things with this tape, and that's going to give us numbers. And we're going to use those numbers to plot points on a graph, on a Cartesian plane. And when we have those points on the graph, we are going to try to figure out a function that approximates those points. This is the overall idea as teachers that we're trying to get across. And that function will be a mathematical model of the data. I should say there are many aspects of mathematical modeling. This is just one of them, but it's one of my favorites. Using a function to approximate data points to show what the pattern is that the data points have. So I'm looking at this and I'm thinking, what can I measure? Well, one thing I can measure is the length of these segments. And I'm going to, in the book, this is called a triangle ladder. It looks kind of like a ladder, except that the sides of the ladder aren't parallel like a regular ladder. In fact, they join here at point P. And so I'm going to call these things rungs, like the rungs of a ladder. And I can measure them. And like this one, you can tell this is a United Statesian thing because I have inches as well as centimeters. Actually, most United Statesian tapes have only inches. But I look at this and I will try to measure it in centimeters, and it looks like, oh, it's about 8 centimeters. And so I'm going to grab a different color and I'll write 8 by this rung. And let's measure this one. And this is 10. If you're doing this on paper, of course you do it to the nearest millimeter. It would be 10.3 or something, but this is, well, this one is 13.5. 13.5. Oops, you can't read the 3 very well, and see how long this one is. And this one is 23. Right. And so those are the measurements of the rungs. And now I'm interested in, well, what else could I measure? I'm looking for a relationship. And excuse me, I have to look at my notes because they have just turned themselves off. Because I'm looking to find some sort of mathematical investigative question. And I want to say, how is the length of the rung related to, you might say, what? Well, in this ladder, we have the rungs and we have the sides. So I could say, what is the relationship between the length of the rung and the length of the side? Now, I'm speaking to you as teacher to teacher. If you're inventing something like a new activity for the students to do, this is the kind of question you should be asking yourself. I'm looking for something that will give me a relationship that connects to my actual curriculum. And in this case, I'm imagining I might be a teacher in pre-calculus or in geometry or something where I want to help students make a connection, in this case, between the geometrical situation and what we're going to see in the data situation. That is, we want them to have multiple access to the situation itself, multiple representations. So this is one representation, a diagram. And now I'm going to try to measure the side. And here we are faced with a really great problem for the students. And I like to leave this open-ended for as long as possible. But the question is, well, on the side, what do we measure? One answer is measure the distance from the point to this point, and then measure this distance between these 2 points, and then measure this distance between these 2 points. And if you do that, there will not be a clean relationship. If some students do that, personally, I think it's okay, because we would be sharing our work in the classroom if we're in person. And it's easy enough for people to sort of correct what they have done and say, oh, maybe it would be more interesting to do it a different way. There is nothing wrong with measuring this way, but you won't see an interesting relationship. So I'm going to step in and say, we do some experimentation, we try different things. Some students say, oh, let's measure from this end. Some students say, let's measure from point P. And I'm going to say, yeah, let's measure from point P. And so I need another color. I'm going to use blue. And I'm going to say, what's the distance from point P to this line to the dot along that line? And so I'm going to measure this one, and I say, oh, this is like 8.5. And I'm going to put the distance to here like this, 8.5. And personally, I really like actually writing on the diagram, if you possibly can. And I'm going to measure this one, and this is 12. It's very hard to write legibly on this thing, but I'm doing my best. Now we'll measure to the next one, and that looks like 18 and a bit, but I'll just write 18. And the very last one, I'll measure to this dot out here. And this is 28.5. Okay. What? Oh, come on. 28.5-ish. So at this point, I have actually 4 ordered pairs. I have 8.5 and 8, 12 and 10, 18 and 13.5, 28.5 and 23. Everybody okay so far? I can't see everyone's face, but if you indicate by a few people by nodding or something, can everybody see what's going on? Everybody okay? Okay. Thank you, Chippo F. However you would say your name. I appreciate that. Yeah, so great. Thank you. So this is this geometrical situation. And if you're teaching geometry, you could ask your students to say, what's the geometrical relationship between these things? How must these numbers be related? And if your students are like my students, if they are not currently taking geometry, they might be a little puzzled. So what we're going to do here is we can approach it either way, but we're going to approach it through data. And in order to do that, I'm going to share my screen. And so you remember what this is like, or you have your own, and you can enter the data, but I'm going to share my screen, and we're going to go to CODAP. Now, just to remind you, if you just joined us, codap.concord.org/app. Or if you Google CODAP, C-O-D-A-P. Oh, yes, and Pip has just put the full URL in the chat, which is fantastic. So I'm going to share my screen and show you what it looks like. So this is what a CODAP screen looks like when you first enter the app. And it says open document or browse examples, create new document. If you did open document or browse examples, and I'm not going to do that now except to show you what it looks like, you will see that there's a document here called Getting Started with CODAP. And if you've never looked at CODAP before, do that. And that's a really good way to get oriented to CODAP. That's what I do with my students. But I'm going to cancel that because I just want a new document. This is a brand new document. So we're starting fresh. And in order to make a data table, I go here to tables and I say, not new from clipboard. If I had data in the clipboard, I could do that. But I'm just going to say new, and it says a new attribute name. I'm going to say triangle ladder is the name of the data set. And now I'm going to go to where it says attribute name, and I'm going to rename it, and I'm going to call it rung. Could be rung length or something like that. And this plus sign right here, I don't know if this is getting larger for you to see this plus sign. If I click it, I get a new column and it's ready, and I'm going to type side. So I have headings for my two attributes. So this one is rung, this one is side. If I need to edit it, I can change the attribute properties. That's how you change it. And in fact, side, I'm going to say the unit is centimeters. I can give it units this way. I'm going to do the same at rung. I'm going to do edit attribute properties. I could change its name to rung length, and I'll say the unit is centimeters. I can give it 2 decimal points of precision. That's all right. And I'm now, you cannot see my little whiteboard, but I'm going to read the rung. The first rung we had was 8, and the side measurement was 8.5 centimeters. And I'm pressing tab and it's opening up a new one. Then I have 10 and 12.5. And now I have 13.5, tab 18, tab 23 is the last rung, and 28.5 is the last side measurement. So I have this little spreadsheet, the table of my data. And now in CodeApp, I'm going to make a graph of this. So I click graph, and I get that. And those of you who've used CodeApp before, remember that what we're going to do to make a graph to help students organize these randomly organized points here, in order to organize them, we're going to label our axes. And now we have an interesting question. What should we put on the horizontal axis? And I'm not quite sure what, but I do want to point something out at this point. If you have a chance to look at the little tiny pictures, that it includes a little picture of me and you can see the diagram, we've now converted our mathematical representation from the geometrical form over here to the tabular numerical data form. So we've used 2 different representations. And I have chosen as a teacher, that we're going to start analyzing this situation with the data representation rather than the other one. So how can I work on the relationship between these 2 quantities? Oh, a really great way is to make a graph. And I'm going to just decide arbitrarily to put the side on the horizontal axis. And there are the values of side. And now I'm going to put the rung on the vertical axis. And I think you could go either way, but I'm going to do like this. And I look at that and I say, it looks like there's a relationship here. And depending on...
That is fine, thank you.
Say again? Oops, well, all right. Depending on the sophistication of your students, they might have a very clear idea of what this relationship is, or maybe all they can say at this point is, oh, the longer you go up the side, the longer the rung is going to be. At this point, you can stop for a moment and say, does that actually make sense? Because I'm now going to point again, and you look at the diagram, and of course it makes sense. The longer you go up on the side, the farther apart the 2 rays are, and the longer it is to go along the rung to get to the other side. And so this is the beginning of actually explaining what the situation is, justifying what's going on. So, but we, of course, would like to go further with this and say, what is a mathematical function that matches this? Well, we have some tools in CODAP in the ruler palette. A really great one is the movable line. So I'm going to click on the movable line. And a thing I love about the movable line is that you can move the parts of it, including its formula. And as I drag it, the formula changes as I drag. And I can say this looks kind of it might be curvy. I actually have mathematical insight, so I know it's not supposed to be curvy. It's just that my measurements are really sloppy. But I could say, you know, if I were at 0 side length, I should have a 0 rung length. So I believe that this line ought to go through the origin. So right now it says rung is 0.781 centimeters per centimeter, 0.781 times side plus 0.1. Maybe I can get it to 0. There's 0.02, 0.09. Can't quite get it to 0, but this does give me a chance to look at this line and say, huh, is this an okay model or not? Now, I might look at this value and this value and say, you know, maybe these two are out. Maybe I should remeasure. I will not do that right now because we're zooming through this. We have very little time. But this is a great place for students to think about the precision of their measurement, to review it, and then to say, well, if this is in fact a straight line, and if it in fact goes through the origin, what does that possibly mean about the situation? And I don't know, someone tell me something. What the fact that it might be a straight line? Well, first of all, how do you feel about this? Do you think it's a straight line? And second of all, if it is a straight line, what does that say about the situation? We should hear someone's voice other than mine at least once or twice during this session. I'm trying to use wait time, but I don't know if you're having trouble with audio.
Somebody's put something in the chat saying a linear relationship, a couple of linear relationships.
Great. It's a linear relationship. Yeah, right now I can't see the chat. Oh, good. We're getting some more things in the chat. Yes, thank you. Great. Okay.
It's a positive,
and then John, go ahead.
Positive and linear relationship, quite strong relationship.
Yes, it's positive and linear. And Zahn also says directly proportional. We'll come back to that in a moment because Natara perhaps is the name. As the side length increases, the rung length also increases. Yes, absolutely. Increasing function. All of these are great pieces of vocabulary that are helping students understand what's going on and let them use that vocabulary. And now I want to go right back to Zahn, who said it's directly proportional. Yeah, strong, positive, and directly proportional. If it's directly proportional, that means there's no intercept, right? It's really rung is a constant times side, and there's a direct proportion. And I just want you to imagine, again, as we're going so quickly, that we have some more time to let this sink in. But this is a place right here where we can now return to the diagram and think about the geometry. And so I'm going to, I want to keep this picture in your mind, which we could do if we had in an actual room together, but I'm going to stop sharing and we're going to look back over here and we're saying this distance is directly proportional to that distance. And the fact that 0 goes through 0 makes perfect sense geometrically. So we have this data thing with the graph, and the graph helped us see it was directly proportional. And now I want to return to the geometrical representation and say, what's the connection between this and direct proportion? And if you're like my students, they have some sort of little tiny linguistic connections that they can make, even if they don't fully remember what happened in geometry. And one of the things they'll say is something like, oh, well, in similar triangles, things are proportional. To which we will say, oh, that's an interesting comment. What things are proportional? And they might dig deep into their lost memory and say, oh, it's like there's this corresponding side thing. And I don't know what the words are that you use in New Zealand for this, but here in California, the law is in similar triangles, corresponding sides are proportional. And there is a constant of proportionality that relates the corresponding sides. So when we looked at our graph and we saw the slope of that line, that's the constant of proportionality. And so we can ask the students, wait a minute, I see two lines and then a bunch of line segments. You're talking about similar triangles. Where are the triangles you're talking about? And so we will get them to actually come up here and say, well, like there's this triangle and this triangle. We say, are those two triangles similar? They say, well, I don't know. They look kind of similar. Well, how do you know whether two triangles are similar? Can you prove that they're similar? What's required to prove that two triangles are similar? And depending on where they are in their studies, they might say, well, if they're similar, that means all the angles are the same. And someone might say, well, if all the angles are, no, you only need two angles to be the same. Well, are the angles the same? Well, one of the angles is the same because it's in common, the vertex angle of this figure. That the other angles are the same is a theorem that we call Zorro. You have parallel lines and then you have a transverse line going across them and corresponding angles are congruent so that we know that, let's change colors, so that we know that this angle is the same as this angle, for example, and that, yeah, the triangles are similar. So we've rocketed through this much more quickly. I mean, we really only spent about a little over 15 minutes on this very activity and thinking about what actually happened when we did this, and especially if we could do it more slowly. And think about the fact that we had two different representations of what's going on. We expressed the situation mathematically in two different ways. We approached it through data. You could have, if you already knew, if you were fresh in your geometry, you could have approached it this way and said, if I measure them, what kind of graph will I get? And predict that you're going to get a direct proportion. And then you measure it and you see the direct proportion and find out, oh, the slope is the constant of proportionality. So we investigated, in our case, though, we investigated the question using data, and then we got a data-oriented explanation. I'm going to share my screen again just really quickly so that we remember what this looks like. This sort of data-oriented explanation. Look, we have a very strong relationship. It's linear. In fact, it's directly proportional. And this would enable us to make predictions about the future. Oh, if I had a side that was 100 centimeters, how long would the rung be? And the answer is 80 centimeters. And we could imagine doing that and actually be using mathematics to make the prediction. In this case, we're just using data, but we also have the connection to geometry. Interestingly, the way I look at this, geometry is the thing that actually explains what's going on. The data don't actually explain why the relationship is this way, but to really justify why the relationship is a direct proportion, you really need geometry. And so this is a great way of students getting to integrate different parts of their mathematical upbringing in order to accomplish something. In this case, this mathematical investigation, where they make sense of the situation, actually in considerable detail. Okay, I'm just about to move on to the next activity, and I'm going to wonder if you have any questions. Positive gradient slope. I see things in the chat. Now I've got my chat back up, and I'm going to stop sharing to get so you see my face again. And I'm also going to grab this. So this is the cover of the book many of you have. So this is the letter-sized United Statesian version. And I want to now look at this page, which you might have been instructed to print out. And so this is this activity called Spiral 20. And the idea is, and I'm going to put this up here, that there are these rays that are 20 degrees apart. So there's a total of 9 spaces to go 180 degrees. And the first triangle, or actually the 0th triangle, is already filled in, delta 0, triangle 0. And what has happened is, we started out here and we turn 90, we go out the ray and we turn 90 degrees and go until you hit the next ray. So we've made a right triangle, and this is the hypotenuse that is longer than this initial leg. But now I'm going to go out this ray, the second ray, and when I hit that spot, I'm going to turn right 90 degrees. Am I turning right? No, I'm turning the way you see it, you turn left 90 degrees, pardon me. I get out here and I turn left 90 degrees and I go until I hit the next ray. All right, so far? This makes a new hypotenuse for this new right triangle. And then I start here and I go do. I turn left, I go out, except it's not drawn this time. You have to draw it. And the relationship I'm interested in is you can see these lengths are labeled. Like this first one is L0 because it's the leg of triangle 0. And this hypotenuse of triangle 0 is the leg of triangle 1. And so this is triangle 0, this is triangle 1, this is triangle 2, and so forth. And what I'm interested in is what's the relationship between the length of the leg and the number of the triangle. And so what I'd like to do is, and everybody's printer might be a slightly different length, different scale, but we'll take a risk here, and I'm going to share my screen again, and I'm going to make a new document in CodeApp. And I'm going to let's create a new document. I'm going to make a new table, and here it's new, and I'm going to do the very same thing I did before. I'm going to edit the attribute properties, and I'm going to say triangle number, and apply that, and I'm going to make a new one, which is called leg length. And I'm going to put triangle numbers 0, 1, 2, 3, 4, 5, 6 here. And now I'm going to ask, let's see, I have to get my chat open again because I just changed things. I want somebody, all of you, if you wish, to measure the leg L0 of triangle 0 and tell me how long it is to the nearest 1/10 of a centimeter. And some of you might get different values for all kinds of reasons, including having a different scale when you print it out, but it should all be kind of okay. And of course, once we get to triangle 2, you will have to have actually made that 90-degree turn, and you won't, I've sort of given you L0, L1, and L2. But when you get to L3, it's going to depend on actually doing some of that construction, the geometrical construction. Do I care that you will not be perfectly 90 degrees? No, I do not. Having a little bit of inaccuracy is something that will make our life more interesting. And while you're doing that, I'm going to keep talking and let you know another thing that's a wonderful thing when you're doing modeling like this is I'm going to make the graph in advance. And so I'm going to put the triangle number here. And if I make the graph in advance, as we get the data, we can start to see what the relationship looks like. And we're going to need to do this fairly quickly, it turns out, because we have to be done at, and I'm going to ask Pip, it's really 45 or 50 past the hour or something like that. Yeah, she nods. So I'm not seeing any measurements of triangle zero's leg in the chat. If I use the one in the book, which is all the way here in the United States, it's something like 9 centimeters long. But yours may be different. Okay, Pip says 8. And we want it, is that 8.0, Pip? Because we are going to go, this time we have to be precise enough to get to the nearest 1/10 of a centimeter. We want millimeter level work here. 8.0, all right. And others, if you disagree, go ahead and enter a different value. That would be fine. I'm going to put the leg length on the vertical axis. And now it doesn't show me the other ones because there's no leg length. So somebody measure triangle 1's leg. The pips came out smaller. I wonder if I get this one, that's 9 point. It's going to be okay. So Evav, you said 7.9. You're going to need to also be sure to let me know what triangle it is. I assume that's also triangle 0.
Oh,
Or was that 1? Oh, Pips was 1. Oh, 8.0. Somebody has to measure 0 then. So Evav, was that 1? L1 is 8.4, says, okay, triangle 1, good. Great, oh, this is cool, this is wonderful. Okay, and now I have Natar JM says 1. Yeah, well, it'll depend on the size of the print. Yes, it will. And so, and I'm going to add a new column for who, just in case, and this is, who said 8.4? Natara. And this is Pip. Pip. And this is Evav.
so Natara is Mala, actually.
Really?
Mala, yeah.
Okay. Yeah, San is absolutely right. It will depend on like your printer and things like that. And I'm worried that we're going to run out of time. We got to get some 2s out here. Someone should measure some of the zeros, L0. L3 is 9.2, and that's Pip. 9.2 Pip. Ooh, look at that. L4. Oh, wow. 4 is 9.9. Is also Pip. L5, 10.6 is Pip. And L6, 11.3. Good heavens. She's filling them all in here. Rest of you, don't let her do everything. Okay. Evav, make sure you tell us which one it is. L7 is 12.1. L8 is 13. Whoops. 8 is 13, which is pip. L9, oops, L9, oops, 9 is 14.1, which is pip. And we're going to take a couple more here. Oh, yeah, 6. Great, great, great. Excellent. 6 is 11.4. This is EVOB. So at this point, you can now see my graph here. And Pip has done many of these. And just by the way, suppose I wanted to keep everybody's data separate. I can drag who to the middle of the graph. And now all the orange ones, these are Pip. And we don't have L2 from Pip, right? No. Okay. But look at that relationship. And we could, 10 is 15.2. Cool. 10. We don't know who did that. No, it's IVOP. Good. 10, 15.2. And Pip is at 8.5. Cool. 8.5 Pip. And so we see this nice relationship, and EVOB's measurements are fairly close to Pip's. We could do, oh, good, 7.7 she has. So 7.7 Pip. So we have this lovely relationship here. And I'm going to go ahead, we'll stop collecting data, and I'm going to start doing analysis, and I'm going to put in a movable line. Whoops, that was a movable point. Don't want that. I'm going to get the movable line, and I'm going to look and say, wow, does this look like it's a straight line? And at this point now, we have more precise data than we did last time. We're fairly sure that these are accurate to within at least a couple tenths of a centimeter. And if that's the case, these dots are above on this side and above on that side and below in the middle. This is a curvy thing. And so we can ask students in what in the United States would be a pre-calculus class, when you're studying elementary functions, what sorts of functions do you know that are like this? And there are many different possibilities. It could be the bottom of a parabola. It could be part of it's like 3 minus cosine, that kind of thing. Any number of different things. But in this case, let's suppose that we get the right answer because there's not enough time to get the wrong answer, and say, maybe this is exponential. So if this were an exponential function, there are many ways we can write an exponential function, e to the kx, that sort of thing. But the one I'm going to use this time is where we might have an opening coefficient, a times a base, b, to the x power. And I'm going to show you how to draw a function in CODAP. I'm going to go back to the ruler, and it says, oh, plotted function. Great. And now there's a little white area up here, and in here, I'm going to enter my formula for the function. And I'm going to say it's a, and I wish I could, if it were Desmos, and you can do all of this in Desmos, it's really fine. I could write a b to the x. In CODAP, I actually have to put in the implied multiplication. It's a times, and I'm going to go ahead and put in b, but really it's triangle number. So I'm going to say triangle number to the x power. And so I'll just click. No, AB, that's not right. I want a times b to the x is the triangle number, b to the triangle number. There we go, a times b to the triangle number. And so I click apply and nothing happens. That's because it doesn't know what a and b are. What I'm going to do is I'm going to go up here and create a slider. And one slider I'm going to call A, and it currently has a value of 0.5, which is wrong. And now I'm going to make another one, which is B, which is the base of the exponent. And that's also going to be 0.5. Whoops, B. And now, although you can't see it, there is a function. There it is. It's down there. I'm going to make the movable line go away so we're not deceived by it. We say, oh, this is 0.5. times 0.5 to the x power. So, okay, yeah, that seems about right. And I can change the shape of the function by moving the slider. And we can say to the students, what happens when you change a? And the answer is when you change a, the whole thing gets multiplied. And importantly, the intercept goes up. And so when I set a to 6, I say, oh, what's the intercept? It's 6. And we say, does that make sense? Do you say, sure it does. Because if the intercept is where triangle number is 0, b to the 0 is 1. And so the value of the function at the intercept is a. Well, I know what the value of this function is. It's supposed to be 7.7 to go through Pip's point. So I'm just going to type in the value 7.7. And that should make it go through the first point. So I press enter, and there it's going through the first point. Now I take b, and I just scooch it. Oh, that's too far. That's too far. I need more control. So I hold down Option or Alt, and I'm zooming into this axis here, this center axis. And now I have lots and lots of control.
Thank you. So,
and this is not a bad model for the function. It looks a little off, but it's kind of pretty good. Now, I want you to remember this function and see it there being not bad. I mean, it looks like maybe I could, if I made it a little bit larger and made this lower, maybe there's something, yeah, it could be, maybe the value of 0 might not be exactly right or something, but I can get a pretty good approximation to the function using an approximation to the data using an exponential function. So I say this is a pretty good model for the data. Now I'm going to stop sharing so we can think about geometry directly. And we're at 48, we got to stop soon. And so the question is, in this picture, what's the geometrical situation that holds forth here? And the answer is surprisingly close to what we talked about in the last one, because all of our triangles should be similar. Because the vertex angle down here are all 20 degrees, and then we have right angles. We've got two angles the same, which means the third angle has to be the same because the sum of the angles is 180. So all these triangles are similar to one another. The difference is that each of these triangles is built on the previous one. So the scale factor, which looks like it's 1.06 or 1.07, is the difference, the factor that relates this leg to this hypotenuse. When this hypotenuse becomes the next leg, when I take this to get to here, I multiply by 1.06. To get from here to here, I multiply by 1.06 again. And from get to here, L2 to L3, I multiply by 1.06 again. To get to Ln, I multiply by 1.06 to the nth power. And that's what gives rise to an exponential function in this geometrical situation with this pretty spiral. What is the ultimate meaning of the 1.06? We say, how can I explain it? How can I come to really understand the situation? To do that, we back up all the way to SOHCAHTOA trigonometry, and we say, oh, there's a relationship between the hypotenuse and the leg, the adjacent side and the opposite side, and that angle 20 degrees. And so 1 over the cosine of 20 degrees is about 1.06. And that's where I run out of time. And so I should stop and take any questions you might have at this point. It gives you an idea of how to connect geometry to data via this modeling process and give kids a chance to integrate some of the things that they learn maybe in different math classes. So thank you for the props, Boros and Teresa. Any other questions from anyone?